last speaker in this realm is Dr. Aditya Grover from UCLA. He's an assistant professor in computer science, where he leads the machine learning intelligence group, or the MINT group, where they develop AI systems that can interact and reason with limited supervision. He has developed one of the more advanced foundation models in climate, called as Climax and Stormer, via the ML for Climate initiative. With that, Aditya, please go ahead. I think Venkat, his video is blocked.
It should work now. It should work now, yeah. We just... Hello.
Hi, everyone. Am I audible?
Yes.
And let's just do a quick check of my slides.
There seems to be a bit of a bandwidth issue or so, because it's very slow to come up, even opening the slide. Stuck. Turn off this one. Is it a problem on our side or?
Oh,
Okay.
can you guys see my slides?
Yeah, can you hear us now?
I can hear you guys. And is it the presenter view or is it the correct view?
It's the other one you
It's presenter view right now.
Okay.
swap this, please.
Hopefully this one's better.
Yes.
Yep.
Thank you.
Okay, awesome. I'll start. And unfortunately, I also have a hard stop at 1:30 in 30 minutes. So, but I'll try to, I think we should be able to finish by then and also leave some time for questions.
Great.
So it's great to be here and thanks for having me. And I've titled this talk for thinking about foundation models for a wide range of domains. Centered around sustainability, but starting with something more narrow in atmospheric sciences. So hopefully the vision with which I want to lead this talk is that even though we expect to see foundation models being applied to a lot of scientific domains, there's also this emerging question of how they can interact with each other. And through atmospheric sciences is one attempt at solving a wide range of sustainability problems. So with that, let me start why atmospheric sciences, what motivates us. And the last year was the hottest on record. And this year seems on track to beat even what last year's trends was. So there's no part of the globe which has not faced an extreme weather event. So much so that where I am currently at UCLA, there was so much rainfall in February this year that comparisons were being made between LA and Seattle. And anyone who's lived in SoCal would know that's not something we would ever want to hear. So with this, there's this question of like, how can AI help? My background is in computer science. I'm a computer scientist by training, and most of my career I've spent working in generative modeling. And generative models having much more better news compared to what we saw with atmospheric sciences when it comes to thinking about what the impact is having on the real world. There's a lot of positive advancements in language, vision. My own group works a lot in the intersection of generative models and decision making. And looking at all these advances, one also thinks what's there for science. Science, as we've seen in talks all through today, is also having reaping the benefits of many of these advances, AlphaFold being the primary example of that, and many such models since then. So the question today we'll be wondering is, does this foundation model paradigm also influence atmospheric sciences at large? And with this, we would think about what are the algorithmic primitives which will help us design what I call as atmospheric foundation models. Now, to dissect what this means, the very first question that comes to mind is what exactly is a model? And if you ask a computer scientist or someone who's worked in machine learning specifically, the word model is also one of debate. So in traditional machine learning, we were used to this paradigm where for any given task that we cared about, we would collect data, train a machine learning model, and then deploy it to solve that specific task. But more and more, what we see with systems like ChatGPT is there isn't task-specific models, but what we have is a foundation model that's trained on a very wide and diverse data source like the internet or on YouTube. And then this model can solve a range of different tasks for defined over a broad domain. So, but if you go to an atmospheric scientist, the word model evokes a very different picture. For an atmospheric scientist, a model typically refers to a physical model, so essentially some system of differential equations that governs the flow of energy and mass through the system. And this is a technology that's been one of the most wonderful things that science has given us in the last few decades, and something that was also acknowledged in the Nobel Prize in Physics very recently. And it's a technology that's also been steadily improving. So from the early days of numerical weather prediction in the 1980s to where we are today, if you look at the forecasting skill for different lead times of predictions, predicting 3 days ahead, 5, 7, and 10 days, we find that for both North and South Hemisphere, there has been an improvement. In fact, there's virtually no difference between the two hemispheres right now. And we see that we actually have much more reliable forecasts today than we did a few decades ago. Yet, there is definitely more potential. So if you look at the question.
No. Let's keep going.
So if you look at this threshold for what's considered as high skill, we still have high skill for about 5 days predictions on a certain variables like temperature. But then many other variables, or even for variables like temperature, if you want to make predictions for higher lead times, there is still very slow progress. And given the pace at which we are seeing extreme weather events, we cannot simply rely on this technology, which seems to be saturating or plateauing to some extent to get us to the kind of advancements we need today. So to understand then how can we try to fix this problem, it's worth going into why physical models don't work as well for different scenarios as we would expect. One is, of course, physical knowledge is incomplete. As soon as we go to smaller subgrid scales, it's harder and harder to characterize exact physical processes in motion. It's also one which is a luxury of a few. There are very few national labs in the US and around the world which have access to this technology. And if there's one thing that we have learned from machine learning community is that having a democratic process where a lot of people have access to a technology is really good for science. It vastly accelerates the speed of development. This isn't possible with physical models because they can only be run on supercomputers. And lastly, I would say that even though weather and climate are so fundamental to a lot of aspects of our everyday life, from agriculture to energy to insurance and whatnot, there is very limited interactions between the field of physical modeling and what all these other related disciplines could benefit from in terms of the raw data that's used to construct these kinds of models. Now, foundation models as a paradigm is poised to address precisely these limitations. So foundation models, they scale very well, not just with more compute, which is also true for physical models, but they also scale very well with increasing amounts of data. And given the speed at which we're collecting a lot of these atmospheric data sets, particularly through remote sensing, this is a really good opportunity to address this limitation. Second is The training of foundation models can be expensive, not as expensive as what it needs to run these physical models, but still relatively it can require non-trivial amount of GPU resources. But at the end of the day, it's still a one-time cost. Doing any kind of predictions or fine-tuning on top of it is quite inexpensive. And the last is the whole paradigm of foundation models is not meant to solve a single problem. Its main benefit does come when we can actually allow these models to adapt in quite a compute and data efficient manner to broad kinds of domains. And that's also something we'll see early evidence of that later in my talk. So what this talk today is going to be about is essentially figuring out what are some of the primitives which enable atmospheric foundation models to generalize broadly. So we'll think about questions on the data side, questions on the model design, as well as how to actually fine tune and generalize these models to different domains. And I think of fine tuning or any kind of generalization, just to make that more concrete, what that would look like for atmospheric foundation models. It could be fine tuning on the temporal scale, so trying to generalize these models to different time scales at which they are making predictions. It could also be generalization in the spatial scale. So for example, in downscaling, you have a low resolution map, and then you want to make it high resolution to inform regional policy and decision making. It could also be things where we go into a related but different domain. For example, if you have a foundation model for weather, can it help us say something about climate? Can it help us say something about agriculture? And those are also axes of generalization, which we want these foundation models to generalize to. So with this, broadly, the talk will have three parts. First is we're going to think about what objectives we can use to pre-train these models, which is the bulky, expensive step in terms of compute. The second part we'll think about is we'll go a little bit more deeper besides the objective into also thinking about the data and architecture that will enable us to do this kind of scaling. And lastly, we'll talk about generalization beyond just weather. So talking about pre-training, so one nugget of interestingness we have seen in our work is thinking about how we can forecast weather as a good pre-training task that shows wide generalizability. So the current state of weather forecasting so happens that it's split between multiple different methods. So if you're interested in making predictions for very short time horizons, the best you can do is just output what's the current weather, and that's called persistence. If you care about very long time scales, you might be interested in climatology, which just looks at historical averaging of different weather variables. In between is where there is scope for science to be very non-trivial, and that's where numerical weather prediction has had such a massive impact on our everyday lives. So when we're really talking about AI being able to work across these timescales, my main interest in is expanding this frontier of predictability, specifically in regimes where numerical weather prediction or the physics-based approach has been dominant. And interestingly, we want to do that with a single AI model. So we won't be looking at separate AI models for different timescales to start with. Now, forecasting is a very well-defined task, but it's also a task which actually lends itself to many different kinds of solutions. For example, you can have a direct approach where you directly map these kinds of inputs at time t to the same state of the weather at time t plus h. Now, this approach is it's direct. It's in fact called direct forecasting in the literature. But it's solving exactly the task you care about. But then there is a dependence that every time you change your H, you have to have a different model. And even worse, we often have access to, during training, to the state of the weather between T and some T plus H. Because of the fine resolution at which you're sensing, H could be in days, but we have actually hourly records of the weather. So In contrast, what we could do is an iterative approach where we actually break down this problem into a sequence of smaller problems and then try to predict the state of the weather at some t plus delta time ahead. Now, this approach happens to be very similar to actually how autoregressive foundation models like ChatGPT work, where you predict one word ahead and the second word and so on and forth. So there's a closed loop process through which you actually predict multiple time steps ahead in an iterative approach. Now this one, unlike the direct approaches, does use the intermediate outputs as valuable supervision. So that's good about it. But then as you can also imagine, as normal autoregressive approaches are critiqued, there could be compounding errors in this kind of approach. So if you make some mistakes early on, it's hard to actually backtrack or correct them later on. And then there's also this question what delta should be. If it's too small, then you have more chance of compounding error. If it's too large, it starts looking very much like a direct approach. So one of the things we did was in designing a pre-training objective for our foundation model was to think of how can we take these two classic paradigms in forecasting and design a better approach that tries to get the best of both worlds. So we came up with this approach called randomized joint iterative forecasting or RJI forecasting. And essentially it involves two different novelties over the existing ones. One is we start with like an iterative approach, but instead of using a fixed delta, we randomize it. So typically you would take delta to be around 6 hours in prior works. Here we randomize it to be anything such as 6, 12, and 24. So there's both a statistical and a domain-specific reason why we choose these numbers. But essentially, once you do this, you every time you're training, you might be training a model to predict either 6 hours ahead or 12 hours ahead, and this delta goes as input to the model. And then the second thing we did was, instead of predicting just one time step ahead as an iterative approach, even during training, we predict for multiple time steps ahead. So if we fix a delta for a certain iteration of gradient descent, we are not predicting just xt plus delta, but also 2 delta and so on and forth until some k delta. Now this is particularly useful because it prevents the compounding error problem.
So, so Aditya, how do you include delta as a parameter? Is it just one? Is it in the input, or do you give it elsewhere? Do you inject it elsewhere into the neural network, or?
Yes. So essentially, in our approach, delta is the input to the neural network, and the way we feed that as input is to create an embedding of a scalar quantity.
Okay, just an additional scalar input.
Yes.
Okay, thanks.
And then from a domain-specific point of view, randomizing delta is also some value. Like when we use delta, which are 6 to 12 hours, we're essentially learning features that are important for the day-night cycle, right? Like the temperature during the day is very different from temperature during the night. So distinguishing that can happen with low deltas. But then there are also changes which happen at a more longer frequency, above 24 hours or so. And those are captured when we use a higher value of delta. There's also this other aspect of doing joint prediction that I talked about. And like I said, the reason for predicting all these different time steps ahead is to reduce the mismatch between training and testing, because at test time, we may not be interested in just delta ahead. We might be interested in much further time steps ahead. And having that being predicted explicitly during pre-training helps reduce that mismatch. Now, in terms of empirically, I'll first show some ablation results of including these two features, and then I'll show some benchmark results where we compare against state-of-the-art models. So the first one I said about randomization of the delta, and we can see here that our approach, which was called Stormer in red, does much better in terms of reducing the root mean squared error for these weather variables as we choose a randomized version of delta. So on the x-axis, we are seeing what's the lead time we care about, whether we care about predicting 1 day ahead, 2 day ahead, and we go in this plot up to 10 days ahead. And as we increase the lead time that we care about, the randomization approach, in fact, ends up being more beneficial than just choosing a fixed delta. Similar kind of plot here, where now we're looking at the effect of predicting not just t plus delta, but all up to t plus k times delta. And again, here, if we predict multiple time steps ahead, we find similar advantages with k equals 8 as opposed to the default version of k equals 1. Now, combining these kinds of advancements, and we also did comparisons with the state of the art. So I'll just describe some of these methods. Climatology and persistence are the baselines I already discussed. Pangu weather was published in Nature last year. It's one of the state-of-the-art weather forecasting models. And then GraphCast was the effort by Google that came immediately after and was quite in the news as well. And IFS here is what's currently deployed as the gold standard by the European Center for Medium Range Weather Forecasting. And so what we're seeing here are 3 different weather variables: temperature, winds, and humidity. And we're seeing on the x-axis different time scales at which we're making predictions. For all of them, we're measuring the root mean squared error, lower the better. And what we find in all of these plots is the same story, that our approach called Stormer, by using this randomization and joint iterative forecasting, actually ends up doing much better than both the traditional physics-based approach as well as these recent deep learning-based approaches. And the benefits are much more apparent as we increase the timescales. So the further we want to predict in the future, the better we do compared to these existing approaches.
So what does the horizontal line represent, and why is that horizontal?
So this horizontal line is referring to how much in the future we want to predict ahead. You're talking about this one?
Yeah.
Yeah, so this horizontal line is called climatology. So it's a historical averaging in the past. So essentially, after a certain lead time, and this is actually proven by physics, so after 2 weeks or so, there is enough chaos in the atmosphere that you can't do better than just predicting what historical averaging would tell you on a global scale.
Okay,
Right,
that
so-
makes sense. Yeah, makes sense. Thanks.
Got it. Now, so this is the first part of the talk, and then now the second and third parts of the talk will focus on some other ingredients that made this possible. So data is a big ingredient of any foundation model. We have seen that for language through these scaling laws, but there's also some recent work which shows that these scaling laws are also dependent on the quality of data. In particular, this work, which is a bit more recent, shows that if I did not have diverse data, in fact, I was using the same copies of the data, then what you see is the test loss does not decrease as fast as you see through these bold curves. So if you did have non-overlapping copies, then yes, your loss would decrease much faster, and how fast is determined by these scaling laws. But if there's redundancy, then your benefits could be diminished. So natural question for any scientific field, and in this case for atmospheric foundation models, is how do we get this high quality data, which is very diverse and not as redundant, if you do want to enable this kind of generalization? And here, there are some challenges. So unlike language and vision, atmospheric data sets are less diverse. In fact, if you look at atmospheric data sets, they almost look like a video that's playing. But if you look at these videos, there's so much redundancy in these videos. It's clearly a subset of the diversity of videos you would see on something like YouTube. It's less diverse. At the same time, it's actually much more higher dimensional, because here we are not talking of just one weather variables. We have about 100 to 200 weather variables that we're trying to jointly model. And that coupled with the fact that there's a geometry underneath of the Earth, actually makes it much more challenging to work with these. Okay, I think PowerPoint crashed. I'll just try to restart it. Okay, while this restarts, I'll just reiterate the point I was trying to make, which was, yeah, indeed, there is um, much less diverse data for atmospheric sciences as compared to what we have for other domains. And this reduced diversity is a big challenge. So the question is, how do we actually then expand this data? Now, if you look at atmospheric data sets in a bit more detail, turns out there are two different fractions of data set. There's one data set which are called as reanalysis data sets, which are actual observations, which have been combined with some assimilation techniques to create what is roughly a gridded record of the atmosphere for the last 40, 50 years. But then there's this other community that's been generating data sets for centuries. So there's paleoclimatologists who have been generating data which was much further into the future as well as much further back in the past. So they have been essentially taking in very sparse records in the past and trying to extrapolate them to as early as the 19th century. And then there's also this community which is trying to essentially assess the impact of climate change and building lots of climate models which extrapolate much into the future to almost the end of the 21st century. So with all of this simulation data, can we do something to expand what would be the true historical records? And that's something which we explored. So PowerPoint is back up, so I can share my slides again. Yes, so essentially, yeah, so these are the two branches of data we have in atmospheric sciences. So one of the things we did in our work was we started with a curriculum of learning where we first focused on pre-training using data which was mostly simulation based. And then once we had the model pre-trained on simulation data, then we essentially fine-tuned it on real data. So the benefit is these pre-trained data sets.
Aditya, we see your presentation mode now. Not that it's a big deal, but just letting you know.
Okay. Let me try to switch it back. So yeah, so we see these climate model simulation data sets, which are much more expansive than what we have in terms of real data. So we had some more methodological work in the machine learning community, which was looking at the sim to real generalization for transformers, and then we find that it actually extends very broadly to many scientific fields, and this is just one example in atmospheric sciences, where if we increase the number of simulation data sets, the pre-training loss keeps going down. So this loss is evaluated on the real data set. So it's very interesting that just having a lot more simulation data is leading to a reduction in loss for the real test data. So this is one very important axis when we think about how do we expand the data for atmospheric sciences to enable scalable training. Because
sorry, just so we understand what you're saying. So even though ERA5 is just part of the data, including the other data sets that you showed, helped you improve predictions on ERA5?
Yes,
okay.
Exactly. So With this, then we also moved on to addressing the geometry challenge, which is essentially the 3D structure of the data. I'll skip this in the interest of time, but the papers I link below actually have a lot of these details. But essentially what we did was we took the regular transformer and we figured out a way to embed lots and lots of multimodal data sets. And that was really powerful because weather contains hundreds of different variables that we're trying to model jointly. The final part of the talk was going to talk about generalization. So like I said, the title of this talk is Foundation Models for a More Sustainable Planet. So I really think about the impact of this work beyond atmospheric sciences. And essentially that means that we have to think about inputs which could benefit from weather representations, but are not in the same format as well. That includes things like greenhouse gas emissions. That includes things like agriculture. So here is just one example where we were looking at climate bench, where the inputs are actually from the chemist looking at four things in terms of the atmospheric chemistry, which was not part of the pre-training of the model. And the output variables were related, but they were actually had very different semantics from what we were using during pre-training. And we find that there is ways in which we can essentially freeze the middle layers and then just fine tune the initial and the final layers to get this kind of generalization. Now, in the paper, there are many more tasks which are we generalize to. So downscaling, regional forecasting, and so on forth. In fact, since we released this work, the community has used this model for fine tuning for many other use cases like wildfires in agriculture, processing damages to buildings. We ourselves are collaborating with Amazon for using it for figuring out land use patterns in the Amazon rainforest, and as well as with Argonne for predicting extremes. So essentially, what I want to emphasize for this talk is that the intersection of AI and atmospheric sciences is really an engineering science, right? Like we have to engineer systems that work at scale, and the science is not lost there. Once we engineer these systems, we can analyze them to enable new science. And my group maintains an open source library, which allows the interdisciplinary work to flourish in this space. So with that, I'll also leave a question, which I think is on all of our minds, that the bitter lesson repeat itself for AI for science, where we rely less on priors and more on data to enable very broad generalization. It's held its value for language and images, but my bias take is that we might have a bittersweet lesson where we actually have some domain knowledge being enforced into the design of machine learning primitives. So domain knowledge is not completely lost, but yes, the role of scale in both data and modeling aspects cannot be diminished. So with that, I'd just like to thank all my students who did all this work. Thank you.
Questions?
Can you speak a bit about the size of, I mean, I'm familiar with ERA5, but the other data sets, how big are they? Define big in your.
Yeah, so we had them, so they are roughly in terabytes, so tens of terabytes. But we also used 4 data sets to start with, which is a small number. Because this was the first work as a proof of concept. If you go to an atmospheric scientist and they dig up all their archives, they could easily run into petabytes. But that engineering aspect is also one of importance of how do we actually extract diverse data sets and not just everything that we have recorded so far.
The 4 that you started with are the 4 data sets.
Yeah, so these are from this collection called CMIP, which is an ensemble maintained by a lot of climate modeling groups around the world.
It's CMAP?
Yeah, CMIP, CMIP.
Okay. Yeah, I'm sure it's in your papers. We'll look it up.
Awesome. Thanks so much. I do have a hard stop that I'm running late for, but thanks so much for attending
Thank
this
you very
talk.
much. Thank you. Bye.
Thanks,
Thank you.
Aditya.
Thanks a lot.
Okay, so there's actually a hand up. Sorry, he had the. So Paulo,
I
can you?
just saw it. Well, no problem. Unfortunately, the speaker already left. Perhaps I will be able to ask questions over email. Thank you.
Yeah, or you can type your question. We'll be interacting with him again. So if you want to mention what your question is, we can follow up. Or yeah, you can also email him.
Yeah. If there is a minute
Yeah.
here, perhaps this is a question that was on other people's minds. The role or the way physics was, the way domain knowledge was being embedded in this framework seemed to be only through the training data that right that towards the end we got to hear that the simulation data was used to augment the predictive power of these tools. So I was just wondering, I mean, I'm not an expert in climate modeling, but what about efforts in using working with Navier-Stokes on the scale of the planet, but now trying to find out using machine learning to learn closures for unresolved scales. So what is the, I mean, the people in the climate side, how do they see that approach versus what is being done now? Was my question.
Yeah. So that, in fact, we have a direct answer to that question. One of the members of the communities from University of Chicago, he's going to be with us the third week, and that is precisely what he does. And to a smaller extent, even my group does that kind of work, but not for climate, but for fluids in general. There is a lot of work in that activity. In fact, that was one of the first uses of AI in the climate field about almost a decade ago. So there's a lot of such work. And also, you're right in what Aditya showed, the physics really was in the training data, but there are also many other groups that enforce hard constraints like mass conservation and things like that on the data set, on the output of the network. So there are, I think, a variety of tools, and I think that's what Aditya was alluding to in the end, that we have to engineer this system with whatever makes sense.
Right.
But it is kind of interesting to me that this is a pretty, it's almost like a sweet spot application as far as PDEs are concerned, because you're not interested, at least some of the more successful applications in this domain have targeted very short-term predictions. Like you have a storm trajectory, you have initial conditions, can you predict next 4 or 5 days? And for those kind of applications, these tools are like really good compared to, even accuracy-wise compared to solving the equations, but speed-wise, they're many orders of magnitude faster. So yeah, just a long answer that yes, there are many approaches that people use.
Yeah. It's it's a shame I only heard about this school very, very late. Sounds like you guys are going to have very interesting discussions at some point. Karthik, if you are available, I would be very interested in having a quick discussion about what your group does. My group works in plasma physics, and we are doing similar things of coming up with fluid type descriptions of plasmas, where plasmas are these. There's fluid mechanics, but these involve charged particles and electromagnetic fields, etc. Well, thank you all for your time.
Please drop an email. We'll be in touch.
Yeah, thanks.
Great. All right, so that's pretty much it for today. So thank you for everyone for attending. Tomorrow we have the morning session, which is
10
open,
a.m. start.
and we have, I think, 2 or 3 talks there. 5 talks. 5. Oh yeah. Oh yeah. This is the
Found size session.
yeah the foundation model session. So you'll get to see a number of different topics, but shorter talks in the morning. So I hope to see everyone there. And yeah, enjoy the rest of the day. Thank you very much. And thank you, Arvind.
Thank you. Thanks a lot. See you guys.